Dear colleagues, this presentation is dedicated to the estimation of the pressure loss in a straight pipeline. We are interested to cover all possible applications. They are liquids, gases, vapors, saturated or not, with or without pressure. The pipe material can be different and as well its shape. We want to explain here the physical laws behind it and demonstrate the similarity of the theory between different types of fluids, pressure and condition. Eventually, we will come to few different formulas for use in our daily life and we will see their limits of application.
What are head losses? The head loss is happening when a fluid, gas or liquid, is flowing within the pipe, and because of the friction due to the roughness of the walls, the energy is lost. And this energy can be measured as pressure drop. In order to keep the fluid running in the pipe, we need to apply an external work, either by pumps or by compressors. We learn in this video to estimate those losses for liquids, both water and oil, for gases with pressure or less, for straight pipes and also for fittings and bulbs, and for any shape, either round or not round pipes. Here are represented all possible cases, either liquid or gas. Liquid of our interest are water of any temperature and oil. About the gases, we have incondensable ones, like natural gas or air, or even vapors. A special regard must be given to the air ducts for climatization, since they have less pressure and therefore the pipe can be round or even rectangular. Let's speak about theory. For the liquids, incompressible fluids, we define the hydraulic head H as the total energy owned by the unit mass. It is measured in joule per kilogram. And this H is the sum of three energies: the kinetic, the pressure and the potential one. If there are no losses, the head is conserved. In this presentation, we take care of head losses due to the friction in the pipe, proportional to the square of the speed to the length of the pipe and inverse to the diameter as per the formula displayed. The friction coefficient F, this one, is given by the Moody chart, the chart on the right side, and it can be also calculated by the formula in the brackets for the laminar 64 divided Reynolds number, and for the turbulent, when Reynolds is greater as 2300, we have this more complex formula, not dependent upon Reynolds, but only upon the roughness E and the diameter D. And the practical expression of the head loss is in meter, so it is, as per statement, delta H divided by the gravity constant G. The Moody chart seen before says that the friction coefficient F is depending upon Reynolds number if the flow is laminar, otherwise only upon the roughness E and the pipe diameter D. And the roughness depends upon material of the pipe and its machining, as per below, where the values are expressed in millimeters. In addition, we must introduce the concept of equivalent length. If the pipe has elbows, T or valves, they are computed by increasing the length of the straight pipe as per table aside. This table can vary, given just for example. For instance, if we have a pipe of 100 meters and 10 elbows at 90 degrees, the table says any elbow is equivalent to 30 times L over D. We need to increase 30 times 10, 300, times 100, the size of the pipe, 30 meters. So the equivalent length is 100 plus 30. Let's work out the formula before replacing V, the velocity, with the flow rate Q divided by the area, pi d square over 4. And we use the equivalent length LE instead. Then we define the constant K as per this expression. And we come to the pressure drop function of Q square inverse of diameter to fifth and proportional to the length. Actually, K is not a constant, it depends upon F. But if we consider only turbulent flow, which is generally valid for water, F is only depending upon material and pipe size. And if we stay with steel pipes, then E is known, 0.046 millimeters, and K is only a function of pipe diameter, and we can adapt the empiric formula below, while the units are liter per second for the flow, millimeter for diameter, meters for the length, and J is therefore in meters. Let's make now a numerical example. Given are Q, D, length of the pipe, and the fittings. We calculate first the equivalent length, 125 meters. Then we calculate K from the diameter, and we input K, Q, D, and the equivalent length in the formula. And we find 5.48 meter, that is equivalent to 53 kilopascal. Should we have to deal with oil, what is the difference? Actually, the J formula of the previous page is still valid, but what is changing is the expression of F. Since we are now dealing with the laminar flows, F has another expression. Now we plug this expression into the J formula and we get this red one. The constant K1, it does not change, practically a real constant. Here we notice the head loss depends upon linear Q, not any longer square, inverse of diameter to the fourth power, not the fifth, is also proportional to the length, but we have in addition the kinematic viscosity Ni. Now an example. The flow is given, as well the diameter, the length of the pipe, the kinematic viscosity, and the density. By plugging these values into the formula, after calculation of the equivalent length, we come to 56 meters, equivalent to 441 kilopascal, by inserting the density of the oil, 800 kg per cubic meter. We have seen the formulas for the liquids. Now we come back again to the theory in order to find an equivalent one for the gases. The first principle of thermodynamics says the delta enthalpy is equal to the sum of the heat and the work, and the enthalpy is also equal to the expression on the right hand. But since the work is zero and the temperature also does not change for isothermal transformation, the energy conservation says that the specific heat Q is equal to the kinetic energy change. And the specific heat we can also express as heat for unit length times the length of the pipe. From the gas dynamics, we learn also the expression value, where F is the friction factor already calculated for the liquids. By combining the two formulas above, we get the expression 3. The difference among the velocity square can be written as the velocity difference times the mean velocity twice. And using the mass conservation law at position 4 and the gas state equation at position 5, we come to an expression of the delta pressure. And working out this expression by replacing the velocity square, we come to this formula number 7, and combining 6 and 7, the final expression for delta P. This is very similar to the water formula, having the mass flow rate in place of the volumetric one. What is new is the density at the denominator and the constant K2, which is also a function of the friction coefficient F. For steel pipes, we can use a simplified formula for K2, where D is expressed in millimeters. For the gas ducts, we need to rework the equation a little bit. And first, we need to change the speed here by using the mass flow divided by density and the area. In this case, the area cannot be expressed as diameter square divided by 4 times pi, because the duct is not always round. And we will introduce here the volumetric flow by replacing the mass flow as density times volumetric flow. And we get this expression. Cross-sectional area of the duct, hydraulic diameter, which is defined as 4 times the area divided by the perimeter. For a rectangular duct, it is given by this formula where A and B are the sides of the cross section. If the material is galvanized steel, then we can define the roughness E 0.15 millimeters. And by adopting millimeters for the diameter, square meter for the area, kilogram per cubic meter for the density, and cubic meter per second for the flow rate, we can express the constant K3, friction factor divided by 2, by means of this expression, which depends only upon the hydraulic diameter. And therefore the formula for the delta P is given in Pascal. We run now 3 examples. The first is for compressed air. Known are the mass flow rate, the pressure and temperature, the diameter and the pipe length. At first, we calculate the density by the state equation, and we get 9.4 kg per cubic meter. Then we find the equivalent length, adding the contribution of the fittings. From the diameter and the pipe roughness, we calculate the friction factor F and the constant K2. That way we have all the ingredients to fill in the formula, and we get 48.3 kilopascal, almost half a bar. The second example is for a ventilation duct. Here the pressure is atmospheric or nearly, at room temperature. The pipe is not round but rectangular. The length and the fittings are also given. We get first the density of the air, which is 1.18 kg per cubic meter. Then we need to calculate the area, the cross-sectional one, in square meters, and the equivalent diameter, using the formula for the rectangular ducts. And this is expressed in millimeter, 533. By means of the material E 0.15 millimeter and the diameter, we can calculate the equivalent length and also the friction coefficient F, 0.015. Inserting all the data in the formula, we get finally the delta P equal to 178 Pascal. What if we have a vapor? Is the formula for gas still valid? Definitely yes, but with a small correction. We need to introduce Z, the compressibility factor, considering that a vapor is not an ideal gas. For ideal gas, Z is 1, therefore no change. This value we can find in literature for different types of vapors, pressure and temperature range. Given are the mass flow, the pressure, temperature, diameter and pipe length. The material is also given, therefore the roughness E. The density is calculated as per the formula we have seen before, but with the addition of the compressibility factor Z. The equivalent length is also calculated as usual, as well as the friction factor F and the coefficient K2. The formula for delta P is also quite similar to the one used for the gases, with the addition of Z. If the gas is ideal, Z is 1, so there is no change. And by plugging the values inside, we come to the delta P, in this case 31.6 kilopascal. We present here a table, resuming table, with all the formulas seen up to now. The first 2 rows are referring to the liquids. For water and oil, the pressure loss is expressed in meters, and the coefficient K and K1 are represented also here for the simple case where the material of the pipe is steel. For the oil, we remember K is a pure constant. For gases, vapors and any other fluid, either condensable or not, we can use the third row, where zeta is the compressibility factor. If the gas is ideal, zeta is 1. and K2 is given by this empiric formula. If the pipe is not round, which is mostly the case of the air ducts, then we need to use the fourth formula, where the area of the pipe and the hydraulic diameter are expressed respectively in square meters and in millimeters. And the K3, the constant, is given by this empiric formula. The equivalent length is present in any formula and is considering the sum of the actual straight length of the pipe plus the artificial length due to the fittings, and those values are given by manufacturers of the corresponding fittings.
I hope not to have annoyed you. It was some math behind, I know, but it was necessary to understand why. Now you are the expert of the pressure drops. You will be capable to estimate them for different conditions, for a chilled water pipe, for a ventilation duct, or for natural gas feeding stream. Let's have fun.